All right, what we're going to look at now is the comparison of gases at various temperatures, or even the same temperature. And so we're going to talk about how their molecular speeds, so how fast they're moving. And your book has a bunch of equations and derivations for how you can calculate molecular speed. You don't need to worry about doing any of those calculations or knowing those formulas, because the main conclusion from this is that gases move really fast. And the speed that they move depends on the temperature of the gas as well as the identity of the gas. And I'm going to go into both of these properties here. The first thing we're going to look at for this comparison is we're going to compare the same gas at different temperatures. And let's just kind of look at the kind of rough overarching theme of this. If you increase Sorry, I'm having some technical difficulties now. No, I don't want to reboot. All right, I'll just put that to the side. Sorry about that. If you compare a temperature gas at low temperatures versus high, what would you expect their relative speeds to be? I mean, what are you doing if when you increase the temperature of something? You're giving it energy. And so if it has more energy, higher temperatures, it's going to move faster because temperature is a measure of the average kinetic energy. So the more kinetic energy something has, the faster it's going to move. Now, the reason we say average kinetic energy, because if I have a gas at a certain temperature, not every single molecule has the same exact amount of kinetic energy. Some are faster and some are slower. And the way we represent this is let's look at a graph. So on this graph, we have the speed of the gas. We'll put it in like meters per second. And then we'll put a count. So this is like the number of molecules that have that particular speed. Now this curve is going to look different depending on if the gas is at low temperature or high temperature. So let's look at the low temperature conditions here. If it's at a low temperature, then most of the molecules will be at a low speed, but our curve looks like this. Okay, and here's our average. And again, that's for a gas at a low temperature. If I take that same exact gas and I increase its temperature, what do you think this curve is going to do? Well, I'd expect the average to be higher, and I'd expect more molecules to be moving faster. So the curve now flattens out a little bit. And here's my average. This is at high temperature. And so I see that more molecules are moving faster than at a low temperature. So as temperature increases, the curve flattens and goes towards a higher speed. And again, the simple thing to get from this is that a gas at high temperature is moving faster than the same gas at a lower temperature. So if I were to take two samples of helium, put them in different containers, same amounts, and put one at like say 0 degrees Celsius and another at 100 degrees Celsius, then the molecules at moving at 100 degrees Celsius are going to be moving faster than those at 0 degrees Celsius. Now, let's do one more comparison. Let's look at different gases at the same temperature. And in order to look at how the energy is going to compare, let's look at the formula for kinetic energy. You've taken physics, you probably remember this. It's kinetic energy is 1/2 mass times volume squared. And we're going to focus, not volume, I'm sorry, velocity squared. 1/2 mass times velocity squared. And let's look at that mass component to it. And I want you to kind of think about this question. If you have a baseball moving at 25 miles per hour compared to a car moving at 25 miles per hour, and someone said, I'll give you $100, but you got to stand in the way of one of those objects, which one are you going to pick? Well, you're going to pick the baseball. Getting hit by a baseball at 25 miles per hour is going to hurt a lot less than getting hit by a car at 25 miles per hour. And why is that?